Second revision proof I'd like to have a go at for you is this one. It's a proof by induction. So this is the one that I did in a tutorial a few weeks back, but I thought it might be worth going over it again. One of the things that this shows you is that proof by induction is not just for doing summations over sequences of numbers. It's a general proof method, and we'll see it here. So it says, consider this statement. If n is a member of the set of natural numbers starting at 1, then n cubed plus 2n is exactly divisible by 3. Prove this statement by induction. In the proofs that I give you, I will be explicit whether or not I want it by induction or a direct proof. There is a direct proof of this, but it's fairly hard, and I wouldn't set it as a question. But the proof by induction is fairly straightforward. So a proof by induction goes in 2 steps: the base case and the inductive case. So the base case is the first of the cases, the one that we need to get the whole proof started. Remember, proof by induction is the chain reaction proof. So it's the chain reaction proof. And in order to get a chain reaction going, you have to set fire to the first firework, you have to topple the first domino, or you have to buy the first student a curry. But you have to get it going, and that's what this base case is. Let's get the process going. What we do is we consider the very, very smallest element for which our statement makes sense. So if we look at this statement here and say, okay, what's the smallest element of n? What's the smallest value of n for which this makes sense? Well, it's pretty clear. We've specified that it's n1, so therefore the smallest value is n equals 1. And all we have to do, it's very simple, we just have to plug n is equal to 1 into our statement. So for n is equal to 1, that means that n cubed plus 2n is going to be equal, well, it's 1 cubed plus 2 times 1. Well, that's 1 plus 2, which is 3. And that's exactly divisible by 3, which is exactly divisible by 3. So the base case is done. So that means the first domino is toppled, or the first firework has gone off. But now what we have to show is what's known as the inductive case. That's right, the smallest case. The first case. Oops, the first case. Okay. The inductive case is if case K is true, prove case K plus 1 is true. What do I mean by cases? What I mean is if you take this formula and you plug into it n equals 1, n equals 2, n equals 3, n equals 4, each of those is a case. So when I get up to case K, I go 1, 2, 3, 4, 5, case K. If I assume that one's true for some arbitrary k, is the next one true? And if I can prove that that is the case, then I know that 1 implies 2, 2 implies 3, 3 implies 4, and so on. So this is how induction works. If case K is true, prove case K plus 1. So let's have a look at case K. So we assume that k to the power 3 plus 2k is equal to an exact multiple of 3. How do I write that? Well, I write 3 times, and then let's just have some integer I, where I is a member. Well, it just says exactly divisible by 3, so all we need to worry about is that it's an integer. It's probably going to be a natural number, but integers is fine here. It just says exactly divisible by 3. And k is a member of the natural numbers starting at 1 because it's the input to this formula. So we're assuming that k squared plus 2 squared plus k squared plus 2k is 3 times some integer. That's our assumption. We're allowed to assume that. And then we have to prove the next case. We have to prove that k plus 1 cubed, this is the next case after k plus 1 cubed plus 2 times k plus 1, and we've got to show that is equal to, so I'll use my little question mark notation, is that equal to 3 times j, where j is a member of the integer set? Is that the case? Well, let's see if we can make it so. Basically, what we've got to do, our goal is to rearrange this formula now so that it's 3 times something, and that something is definitely a whole number. So let's see what we can do with it. So first of all, let's expand out this bracket, and we get k cubed plus 3k squared plus 3k plus 1. I gave that thought to you in the definition, so you don't necessarily need to remember that's the expansion of k plus 1 cubed. You may have come across it before. Then this bracket here is 2 times k plus 2, and the question is that equal to 3 times j, where j is a member of the integer set? Now this is where we can use our assumption. So let me get a slightly different colour of Sharpie. And what I'll do here is I'll put a red box around that. K cubed plus 2k. Well, I've got a k cubed here and I've got a 2k there. That's cool, because I can replace those with this term. Get a slightly even different colour of Sharpie. This term here, 3i. So what I'm going to do is I'm going to take that and replace it with that. This is typically what you do in a proof by induction. You write out your formula and then you realise that you can use the assumption to simplify what you've got. So I'm going to bring down this 3i, where I is an integer, and then the rest of the formula is going to be, well, I've got 3k squared plus 3k, and then 1 plus 2 is 3, and the question mark is that 3 times j. Now you notice that I've got a 3 in all of my terms here, so I can take that out. So I've got 3 times I plus k squared plus k plus 1. And now I can actually say that this is equal to this, because this term here, this is a whole number. And the reason that I know it's a whole number is that I is a whole number. It says that here. K is a member of n1, so it's definitely a whole number, and therefore k squared is a whole number. K is a whole number, 1 is a whole number, and if I take 4 whole numbers and I add them together, I will get a whole number. This is a whole number, so assuming that the formula is true for K means it is true, true for K plus 1. Therefore, the statement is true. And we are done. So that's a complete proof by induction. The base case and the inductive case. Make the assumption, prove that the statement is true for the next case. Typically you are doing this kind of substitution where you are taking the formula that you have here and you are substituting it in here, and you've seen that also in the other proofs that we've done.